All right, welcome back. So now we're going to approach the question of what's the area? We know how to do the area under a curve. Uh, what about the area between two curves? So in this picture here, I have a function here in blue, f of x, which happens to be my top function, and the other function, g of x, which in this picture, for the area that we're interested in, is the bottom function. It's on the bottom. So we want to derive an approach for if we have two functions f and g, how do we find out this area that falls in between the two of them? All right, we can compute the area underneath of f of x, and we can compute the area underneath of g of x, right? Well, from here it would be this area, and of course the area under f will be this. So we can compute those things. But how do we compute the area in between? Well, there's different ways to approach this, but what we're going to do is take our interval here from A to B. So in this case, it's actually from 2 to 4 on this particular graph. We're going to take this interval from A to B, right? And we want to subdivide it up into a bunch of separate intervals. So at any one point in time, we might be at this interval right here, the ith interval, x sub I minus 1. At x sub I. So we're dealing with this interval, and we want to approximate the area that occurs in this interval only. So the idea is to use the same approach. The idea is to use the same approach that we used with when we were defining definite intervals. And that approach is, let's approximate the area here. Let's approximate the area with a rectangle. That'll be our approximation step there, a sub I. What will we do to get a sub I? Well, we'll realize that this length right here is just the difference between f and g, right? That'll be the height of our rectangle. And the width is just delta xi, the width of our interval. So we realize in this picture that that will be just f minus g. That'll just be f minus g. And so remember our algorithm here, our process, our Sally, is we subdivide, we approximate, we're then going to add everything up. We're then going to take the limit, and then we're going to integrate. Then we're going to integrate. So here we've subdivided it. We're working with the ith interval, and that area will be a sub I, which would be the area of this rectangle here, which would be, in this case, f of xi minus g of xi, right? That's the width or the height of the interval times the width, which would be delta xi. Okay. And so that's our approximate step. Then, once we approximate for one interval, we add them all up so that the actual area will be approximately the sum as I goes from 1 to n of f of xi minus g of xi times delta xi. We then take the limit as n goes to infinity of all that stuff. And I'm not going to write it all down again. But when I take the limit, the xi's here become just x's. And we have that the area will be the integral from a to b of f of x minus g of x. And then the delta x becomes dx. Delta x becomes dx. And so now we have our formula for the integral. We have our formula now for the integral, for the area between two curves as an integral. And so that's what we're going to be using here, using this approach, that we're actually doing the width as the difference between the top and bottom function over the interval of interest. Okay, so that's the formula that we're going to use to talk about the area between curves. Now, very often we're going to want to graph them because we're going to need to see which function's the top function, which function's the bottom function. We're going to need that to be a fact that we can use as we do these integrals. But that's the idea, again, is we approximate by looking at, realizing that in this little rectangle here, that the width, the height of the, width is delta x. The height is just the difference between f and g. Is the difference between f and g. Okay, so that then becomes our area formula in terms of an integral. And so in the next videos, we're going to look at using this